Welcome to my lecture on classification and characteristic curves of second order PDEs. So, we will classify the second order PDE according to the sign of the discriminant s square minus 4RT. So, let us see how we define classify the second order PDE. The classification of second order PDE depends on the form of the leading part of the equation consisting of the second order terms, and this leading part is RR plus SS plus TT, because this is the only part which consists of second order terms. Remaining is Fx by Z PQ equal to 0. No second order terms is involved here. So, this part is called as the leading part. So, the second order PDE, the classification of second order PDE depends on the form of this RR plus SS plus TT, which is known as the leading part or the principal part of the second order PDE. Now, the type of second order PDE at a point x naught y naught depends on the sign of the discriminant, the defined as delta at x naught y naught equal to S 2R 2T S, that is S square minus 4RT at the point. So, we calculate the values of S, R and T at the point x naught y naught and then determine S square minus 4RT at the point x naught y naught. If this S square minus 4RT at x naught minus x naught y naught is greater than 0, okay, then the equation will be called hyperbolic, and if this is equal to 0 we call it parabolic, and if this is less than 0 we call it elliptic. The given PDE may be of one type at a specific point and of another type at some other point. So, it may happen that at x naught y naught it is of hyperbolic type, and at another point x1 y1 it is parabolic type or it is elliptic type. So, the given PDE may be of one type at a specific point and of another point at some other point. Now, for example, let us consider this trichotomies equation uxx plus x uyy equal to 0. So, if you compare this with the standard form RR plus SS plus TT plus Fx by Z PQ equal to 0. So, here uxx, the coefficient of uxx is 1. So, R is equal to 1 and S is equal to 0 and T equal to x. So, delta which is S square minus 4RT, the discriminant will be equal to S is 0, R is 1 and x T is x. So, we get minus 4x. So, delta is minus 4x. Now, you can see at the point for any value of x in the left half plane, okay. Let us say this is your 0 x axis by x axis, okay. So, this is your left half plane. So, your x is less than 0, and in the right half plane, okay, x is greater than 0. So, in the left half plane, that is here x is less than 0, and when x is less than 0 delta is positive, okay. So, delta is positive in this side, okay. Parabolic for x equal to 0, that means on the y axis, that is on the okay. So, here this trichotomies equation is parabolic on y axis, hyperbolic in the left side of the plane, okay, left half plane, and the elliptic in the right half plane, because in the right half plane x is greater than 0, and when x is greater than 0 delta is less than 0, okay. So, at different points in the xy plane, the nature of the partial differential equation is different. Now, a PDE is called hyperbolic, or parabolic, or elliptic in a region omega of the xy plane if the PDE is hyperbolic or parabolic or elliptic at each point of omega. The terminology hyperbolic, parabolic and elliptic chosen to classify PDEs reflects the analogy between the form of the discriminant s square minus 4 RT for PDEs and the form of the discriminant s square minus 4 RT which classifies the conic sections. You know that conic sections are given by this second degree equation Rx square plus Sxy plus Ty square plus Ux plus By plus W equal to 0, and we say that this conic section represents a hyperbola if s square minus 4 RT is greater than 0, and it represents a parabola if s square minus 4 RT is equal to 0. It represents an ellipse if s square minus 4 RT is less than 0. So, by analogy, okay, the of the given PDE of second order, we call the given PDE as hyperbolic, parabolic or elliptic according as s square minus 4 RT is less greater than 0, equal to 0 or less than 0. Now, so the above conic section represents a hyperbola, parabola or ellipse respectively according as s square minus 4 RT is greater than 0, equal to 0 or less than 0. So, this is the reason why we have called the given PDE of second order as hyperbolic, parabolic or elliptic. The terms hyperbolic, parabolic, elliptic are simply the three convenient names to classify PDEs. There is no other significance to this terminology. Consider the second order PDE. RR plus SS plus TT plus fxyz PQ equal to 0, where R S T are functions of x and y only. The Cauchy's problem consists of the problem of determining the solution of this second order PDE such that on a given space curve gamma it takes on prescribed values of z and the partial derivative of z with respect to n, where n is the distance measured along the normal to the curve. Corresponding to this equation 1, we know that the lambda quadratic is given by r lambda square plus s lambda plus t equal to 0. If s square minus 4 RT is greater than 0, then just now we have seen the equation 1 is hyperbolic, and in this case what happens is that the lambda quadratic r lambda square plus s lambda plus t equal to 0 has two distinct real roots, let us say lambda 1 and lambda 2, and so that we have two characteristic equations dy over dx plus lambda 1 xy equal to 0 and dy over dx plus lambda 2 xy equal to 0. Now, solving these characteristic equations, we get two families of characteristic curves, or we call them as simply characteristics of the second order PDE given by equation 1. Now, if it so happens that s square minus 4 RT is equal to 0, then the equation 1 we have defined as a parabolic partial differential equation, and in that case what happens, the lambda quadratic r lambda square plus s lambda plus t equal to 0 has two equal roots. Okay, let us call them as lambda and lambda, so that we get only one characteristic equation dy over dx plus lambda xy equal to 0. When we solve this equation, we get only one family of characteristics. Now, in the case s square minus 4 RT less than 0, the lambda quadratic r lambda square plus s lambda plus t equal to 0 has two complex roots which are conjugate of each other. Then we notice that the characteristic equations are dy over dx plus lambda 1 xy equal to 0, dy over dx plus lambda 2 xy equal to 0. So, these are the characteristic equations in this case s square minus 4 RT less than 0. Lambda 1 xy, lambda 2 xy are complex roots. So, these two give you complex family of characteristics, okay, complex characteristics. When we solve them, we get complex characteristics. So, there are no real characteristics in this case. Now, let us consider the equation by square r minus s square x square t equal to 0. So, comparing with the equation r r plus s s plus t t plus f x by z p q equal to 0, we get r equal to y square here, s is equal to 0, t is equal to minus x square. So, s square minus 4 r t, s is 0. So, we get 0 minus 4 r is equal to y square and t is minus x square. So, we get 4 x square by square, which is greater than 0. Okay. Hence, the given PDE is elliptic everywhere, okay, except on the x axis and the y axis. So, this is greater than 0 if x is not 0 and also y is not 0. Okay. X is not 0 and y is not 0. Okay. This means that this is your x axis, this is y axis. So, on x axis and y axis, okay, on x axis y equal to 0. So, s square minus 4 r t is equal to 0. Okay, this will become 0. Okay. So, we have, so the given equation is PD, the given PDE is parabolic. Okay, same thing happens on y axis. On y axis x is equal to 0, hence s square minus 4 r t, which is 4 times x square by square. So, this is 0. Okay. So, again the given PD is parabolic. So, on x axis, okay, on y axis, okay, the given PD is parabolic, elsewhere, okay, it is hyperbolic. Okay, for all points in the xy plane, for all points in the xy plane other than those on the x and on the other than those on the coordinate axis. The given PD is hyperbolic. Okay, now let us consider the lambda coordinate. Which is r lambda square plus s lambda plus t equal to 0. Okay. So, then since r is equal to y square, s is equal to 0. So, we have y square lambda square plus t is minus x square. So, this gives you lambda equal to plus minus x over y. So, we have two characteristic equations. We have dy by dx plus lambda 1 x y equal to 0, which gives you taking lambda 1 x y equal to x over y, lambda 2 x y equal to minus x over y. We get here dy by dx minus x over y equal to 0, or we can say by dy minus x dx equal to 0. So, we get y square by 2 minus x square by 2 equal to a constant we can take as C1 by 2. So, or we can say or we can minus C1 by 2 we can take. So, R x square minus y square is equal to some constant C2. Okay. Now, if you take other characteristic equation dy over dx plus lambda 2 x y equal to 0. So, we have dy over dx, here we had taken minus x over y, now we take plus lambda 1 x y we take it as minus x over y. So, this is minus x over y and lambda 2 x y we can take as plus x over y. So, this is plus x over y equal to 0. Okay. So, x dx plus y dy equal to 0 gives you x square by 2 plus y square by 2 equal to some constant we can take C3 by 2. So, this gives you x square plus y square equal to some constant C3. Okay. Now, so we get two characteristic families, two families of characteristic curves. One is given by x square minus y square equal to C2, the other one is given by x square plus y square equal to C3. Okay. So, this represents a family of hyperbolas, this family of hyperbolas, family of hyperbolas, and this represents a family of circles. So, the given PDE, okay, for the given PDE the characteristic curves are two families, one is the family of hyperbolas and the other is the family of circles. The characteristic curves or characteristics are given by x square plus y square equal to some constant, x square minus y square equal to some constant, which are the required families of characteristics. So, these are families of circles and hyperbolas. Now, let us consider other equation 4r plus ss 5s plus t plus p plus q minus 2 equal to 0. So, again let us compare. So, then what we have, r is equal to 4, s is equal to 5, t is equal to 1. So, s square minus 4 r t here will be 25 minus 16, that is 9, okay, which is strictly positive. So, the given equation is, the given PDE is hyperbolic for all x y at all points of the x y plane. Okay. Now, let us write the lambda characteristic, lambda quadratic equation. R lambda square plus s lambda plus t equal to 0. So, in this case r is 4. So, 4 lambda square, s is equal to 5. So, 4 lambda square plus 5 lambda plus 1 equal to 0, and its factors are 4 lambda plus 1 into lambda plus 1, 4 lambda square plus lambda plus 4 lambda plus 1. So, this gives you lambda equal to minus 1 and minus 1 by 4. Let us take lambda 1 to be minus 1. Okay. Then the characteristic equations are dy by dx plus lambda 1 x y equal to 0. So, this gives you dy by dx, lambda 1 is minus 1. So, this equal to 0, or dy minus dx equal to 0. So, we can find y minus x equal to some constant C1. Okay. So, this is one family of straight lines. Now, for lambda equal to minus 1 by 4, we get the other characteristic equation as dy by dx plus lambda 2 xy equal to 0, which gives you dy by dx plus minus 1 by 4 equal to 0 or 4 dy minus dx equal to 0. So, this implies 4 by minus x equal to some constant C2, okay, which is again a family of straight lines. So, this is a family of straight lines. Okay. By minus x over C1 is a family of straight lines, 4 by minus x equal to C2 is also a family of straight lines. So, in this case the characteristics are two families of straight lines. Okay. Now, let us go to so this is what we have. Now, let us go to the differential equation zxx equal to 1 by c square ztt. So, here zxx minus 1 by c square ztt equal to 0. So, we have the standard form of the differential equation as RR plus SS plus TT plus Fx by Z PQ equal to 0. So, therefore, R is equal to 1, S is equal to 0, T equal to minus 1 by c square. Okay, this is small c. Okay, so S square minus 4RT, S square minus 4RT is what? S is 0 minus 4, R is 1, okay, and T is minus 1 by c square. So, 4 by c square. So, this is greater than 0. S square is greater than S square minus 4RT is greater than 0. Hence, the given PDE, okay, the given PDE is hyperbolic. For all x y, okay, for all the points x y. And now, let us find its characteristics. So, we have the lambda quadratic is governed by r square plus r lambda square plus s lambda plus t equal to 0. Okay. So, r is equal to 1. So, we have lambda square, s is equal to 0 and t is minus 1 by c square. So, we have lambda equal to plus minus 1 by c. Okay. Let lambda 1 x by b equal to 1 by c and lambda 2 x by b equal to minus 1 by c. Okay. Then from dy by dx plus lambda 1 x y equal to 0, we have dy by dx lambda 1 x y is 1 by c. So, 1 by c equal to 0 or dx we have to take x and t. Okay. So, that other variable t is by is to be replaced with t. Okay. So, that we can do this I am taking as t. Okay. This t is delta square z over delta y square in this standard form. Here it is given by small t. So, here y is actually equal to small t, t is the time. Okay. This is actually a one dimensional wave equation where this t represents the time. So, y is t here. So, this is actually dx plus c dt equal to 0. So, this gives you x plus c t as a constant, say C1, okay. And the other equation is dy is again dt. So, dt by dx minus 1 by c equal to 0. So, or we can say dx minus c dt equal to 0. So, this gives you x minus c t equal to some other constant c2. So, x plus c t equal to 1 and x minus c t equal to some other constant c2. They are the families of characteristics in the case of the one dimensional wave equation zxx equal to 1 by c square ztt. That is all in this lecture. Thank you very much for your attention.